Hello everyone, welcome you all in this video. Today we will discuss about flow of energy and Poynting vector. John Henry Poynting was an English physicist who did work in electromagnetic energy flow, elasticity and astronomy. So he coined the term greenhouse effect. Both the Poynting vector and Poynting theorem are named in his honor. So he gave the Poynting theorem in 1884. So let us discuss the definition of Poynting vector, then we will derive the integral form of the Poynting theorem. So Poynting vector represents the directional energy flux, that is the energy transfer per unit area per unit time, or you can say power flow of an electromagnetic field. So you can define this Poynting vector in the formula. So Poynting vector equals to flow of energy per unit time per unit area. If you combine energy by time as a power, so you can write power per unit area. So the unit of this Poynting vector will be watt per meter square. Now we will start with the Maxwell equations. So we have third Maxwell equation. So from third Maxwell equation, which comes from the Faraday's law. So equation is basically curl E equals to minus del B vector upon del T. If we take the dot product of this equation with the magnetizing field H vector, then you will get H vector dot del cross E equals to minus H vector del B vector by del T. Suppose this is our equation number 1. Now we will use the fourth equation of the Maxwell. So from fourth Maxwell equation, that comes from the Ampere's law, and the fourth equation is basically, you can write curl H vector equals to del D vector upon del T plus J vector. So here D vector is basically the displacement vector and J vector is the current density. Now we are taking the dot product of this equation with the electric field E vector. So you will get E vector dot curl H vector equals to E vector dot del D vector upon del T plus E vector dot J vector. This is the equation number 2. Now we are going to subtract the equation 2 from the 1. So if you subtract equation 2 from 1, you will get H vector dot curl E minus E vector dot curl H vector equals to minus H vector dot del B upon del T minus E vector dot del D vector by del T minus E vector dot J vector. Now we have a vector identity. I can write here del A vector cross B vector equals to B vector dot del cross A vector minus A vector dot del cross B vector. If we use this vector identity in the left side of this equation, so you can easily write here curl sorry, divergence E vector cross H vector equals to minus H vector dot del B vector upon del T minus E vector dot del V D vector by del T minus E vector dot J vector. Suppose this is our equation number 3. Now we will write a term here, that is H vector dot del B vector upon del T. So here we can replace this B vector by the H vector. So H vector dot mu del H vector upon del T, because we have the relation here B vector equals to mu H vector. So by replacing the B vector with mu H vector, you got this relation. Now suppose consider a term del deba by deba t, that is a partial derivative of the h square. So you can write the h square. So deba by deba t, we can write the h square in the form is h vector dot h vector. Now you can differentiate this with respect to time. So you will get del h vector by del t dot h vector plus h vector dot del h vector by del t. So you can write this term as 2h vector dot del h vector by del t. Now if we divide the whole equation by the 2, then you will get 1 by 2 del h square upon del t equals to h vector del h vector by del t. We got this from the use of the differential calculus. Similarly, you can write here E vector dot del E vector by del t equals to 1 by 2 partial derivative, then you can write here E vector dot E, or you can say 1 by 2 deba by deba 2 E square. So this can be written in our previous equation that we have derived here. So by putting these values, we know that the relation B vector equals to epsilon E vector. So in previous equation, that is this one, in equation number 3, so in the right hand side you are having minus h vector dot del B vector upon del t and minus E vector dot, let us write this equation again here. So I am writing that equation here. So divergence E vector cross H vector equals to minus H vector dot del B upon del T minus E vector dot del T upon del T, del D upon del T minus E vector dot J vector. So now you can substitute the values here. So you can write this equation minus H vector dot mu del by del t h vector minus E vector dot epsilon del by del t E vector minus E vector dot j vector. So we have already find the value of this in the A expression. We have find the value of this in the B expression. So you can substitute these two values here in this equation. So I am writing divergence E vector cross H vector equals to, now replace this value, so you will get minus mu by, sorry, I am writing this again, minus mu by 2 del h square upon del t, then minus 1 by 2 epsilon del by del t e square minus e vector dot j vector. So I substitute the values in this equation. Now suppose this is your equation number 4. If we take the volume integral of this equation on the both sides, so we can write this equation again. So taking volume integral on both sides, so we will have here volume integral, then divergence E vector cross H vector dv equals to minus 1 by 2 dy by dt volume integral mu h square plus epsilon e square dv minus then volume integral E vector dot j vector dv. So these are all volume integral. You can compare from the previous equation. In the equation number 4, left hand side the divergence E vector cross H vector. So we have taken here volume integral of this one. Then the right hand side, first term is the minus mu by 2 del h square upon del t. So here we have written minus 1 by 2 del by del t mu h square. Then the second term is the minus 1 by 2 epsilon del e square by del t. So we have taken common minus 1 by 2 outside of the integral, and the first derivative also from the outside of the integral. Inside we have written mu h square plus epsilon e square, and the last term was the minus e vector dot j vector. So we have taken here the volume integral. So now by using the Gauss divergence theorem, we can change the volume integral to the surface integral. So we can write here from Gauss divergence theorem, you can write here volume integral divergence E vector cross H vector dv equals to surface integral E vector cross H vector dA. So if we substitute this value in the equation, this equation, you will get surface integral E vector cross H vector dA equals to minus dy by dt volume integral 1 by 2 mu h square epsilon e square dv minus volume integral E dot j vector dv. Now we know from the Ohm's law, so we can write here sigma vector equals to sigma j vector equals to sigma e vector. So we can place this value in the equation here. So you will get the relation E vector cross H vector dA equals to volume integral 1 by 2 mu h square plus epsilon e square dv, then minus volume integral E vector dot sigma E vector dv. So this term will become now sigma E vector dv. So this is our the final equation. We have derived here. So this equation is basically known as the integral form of the Poynting theorem. So we have written this equation again here. So the left hand side, that is E vector cross H vector dot dA equals to minus dy by dt epsilon E square by 2 plus mu h square by 2 dot dv minus sigma E square dv. So this is the integral form of the Poynting theorem, and each of the term in this equation has a physical significance. So the factor E cross H vector in the left hand side is basically called the Poynting vector, and it represents the direction in which energy is flowing. So we represent it by the variable S, and S vector equals to E vector cross H vector. So the Poynting vector can be used to determine the net power flowing out of an enclosed space. So if the integral of S is positive, net power is leaving the region, while if the integral of S is negative, so power is flowing into the space. So here I will use the pointer. So this left hand side where you have written E vector cross H vector, so it is basically representing our Poynting vector. So this integral, the surface integral of the point vector, is basically representing the direction as well as the flow of the power from the closed surface. Now we will discuss about the second and third term. So the first term on the right hand side represent the total energy stored within the enclosed surface. So the term is 1 by 2 mu h square plus epsilon e square. So the first term in this expression represent the energy stored in the magnetic field, such as in inductor. This is the actually energy of the inductor, and the second term represent the energy stored in the electric field, such as in a capacitor. You are well known about these two terms. We have already used in electromagnetism. Now the second term on the right hand side represents the energy being dissipated within the enclosed surface. So this is the energy that being converted from electromagnetic potential energy into the heat energy, such as in a resistor, and we can represent this quantity by the variable PL. So here PL equals to sigma E square. So again I am going to this equation, integral form of the Poynting theorem. So here are basically three terms in which the left hand side is basically representing the Poynting vector, which represents the total power flow from a closed surface, and the right hand side we have the stored energy in the form of electric and magnetic field, and that energy is decreasing when this power flow is from any closed surface. Plus we have some dissipated energy here, that may be due to the resistor, that may be due to the resistance, and it is given by the sigma E square. So these three terms can be graphically represented. So I have used this. Yeah, you can watch from here. Suppose this is a closed volume in which you have energy stored in the form of electric and magnetic field. So due to the electric part you have energy 1 by 2 epsilon E square, and due to the magnetic field you have stored energy 1 upon 2 mu H square. So this is the stored energy that bounded by a surface. So when energy flowing out from this box, this volume, some energy will dissipated, and the dissipated energy is the sigma E square. So here the sum of this energy dissipated and energy stored will equals the energy flowing out from this closed surface. I think you have got the idea of the Poynting theorem. So Poynting theorem is nothing, it is the work energy theorem as you have studied in the mechanics. So this is the work energy theorem of the electrodynamics. Hope you got the point. Thank you for watching this video.